What if I told you that the force pulling you towards your chair right now isn't actually a force at all? Confusing, isn't it? Gravity. A word that brings to mind images of falling apples and floating astronauts. It's the invisible force that keeps our feet firmly planted on the ground and the planets orbiting the sun. Or is it? You see, this is where things get interesting. In the realm of classical physics, gravity is indeed a force, an attractive one that pulls objects towards each other. It's what Sir Isaac Newton described in his law of universal gravitation back in the 17th century. The more massive an object, the stronger its gravitational pull. This law served us well for centuries, explaining everything from the motion of the planets to the tides of our oceans. But then along came a man named Albert Einstein, who dared to challenge this long-established concept. In the early 20th century, he proposed a revolutionary theory called General Relativity. According to Einstein, gravity isn't a force pulling things together. Instead, it's the result of how mass warps and curves the fabric of space and time around it. Picture a bowling ball resting on a trampoline. The weight of the ball distorts the surface, creating a dip. Now, if you were to roll a marble near that dip, it would naturally veer towards the bowling ball, not because of any invisible force, but due to the curvature of the trampoline surface. Now, replace the trampoline with the concept of spacetime, the four-dimensional fabric of our universe, and the bowling ball with a massive object like a star or planet. That's the essence of Einstein's radical idea. Objects move along the curves created in spacetime by mass and energy, creating what we perceive as gravity. So, Einstein turned our understanding of gravity on its head, but how did he arrive at this radical idea? In 1915, Einstein proposed a theory that would redefine our understanding of the universe. This was the year when Einstein made a leap of genius, introducing the world to the theory of general relativity. This theory was born from a simple yet profound idea known as the equivalence principle. The equivalence principle is a cornerstone of general relativity. It states that the effects of gravity are indistinguishable from the effects of acceleration. Imagine you're in a spaceship that's far from any star or planet. If the ship accelerates upward, you would feel a force pushing you down, similar to gravity. According to the equivalence principle, there's no way to tell if you're feeling the pull of gravity or the push of acceleration. This led Einstein to a revolutionary conclusion. Objects that are free-falling under gravity are actually moving along straight paths in curved spacetime. And what causes this spacetime to curve? That's where Einstein's field equations come into play. These equations describe how the distribution of energy and momentum in the universe determines the curvature of spacetime. In essence, mass and energy tell spacetime how to curve, and this curvature tells objects how to move. Let's consider a planet orbiting a star. According to Einstein, the star's mass causes spacetime to curve around it. The planet, in turn, moves along a geodesic, the shortest path in this curved spacetime. It's like a marble rolling along a curved surface, naturally following the path of least resistance. This was a radical departure from the Newtonian view of gravity as a force pulling objects together. Instead, Einstein portrayed gravity as a curvature in the fabric of spacetime caused by mass and energy. Einstein's equations provided a new way to look at gravity. But were they correct? Did they make predictions that we could test? As we will see, the predictions made by general relativity have been put to the test and confirmed time and time again, forever shaping our understanding of the cosmos. Einstein's theory was revolutionary, but it had to pass the test of observational confirmation. The true power of a scientific theory lies in its predictive capability. General relativity, despite its abstract nature, has made several successful predictions that have been confirmed by observations. One of the earliest tests was the bending of light around massive objects, a phenomenon known as gravitational lensing. Einstein predicted that a massive object, like a star, would bend the light passing near it, much like a lens. And in 1919, during a solar eclipse, British astronomer Arthur Eddington confirmed this prediction. The stars near the sun appeared to shift their positions, indicating their light had been bent as it passed the sun. Another successful prediction was the precession of the orbit of Mercury. For centuries, astronomers had been puzzled by the small but significant shift in Mercury's orbit, which couldn't be explained by Newton's laws of gravity. Einstein's theory, however, accounted for this shift precisely. According to general relativity, the intense gravitational field of the sun warps the space-time around it, causing Mercury's orbit to precess. Perhaps the most dramatic confirmation came with the detection of gravitational waves. Einstein predicted that accelerating masses would create ripples in spacetime, much like a stone thrown into a pond. These ripples, or gravitational waves, would travel at the speed of light, stretching and squeezing space as they go. A century after Einstein's prediction in 2016, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected these elusive waves created by the collision of two distant black holes. The successful predictions and confirmations of general relativity have made it one of the most robust theories in physics, but it also led to some surprising conclusions. The bending of light, the precession of Mercury's orbit, and the detection of gravitational waves all serve as powerful validations of Einstein's groundbreaking theory. But they're just the beginning. The full implications of general relativity are still being explored, leading us to black holes, the Big Bang, and the very edge of our understanding of the universe. Einstein's equations led to some mind-bending predictions, including the existence of regions of spacetime from which nothing, not even light, could escape. These regions, known as black holes, are one of the most intriguing predictions of general relativity. A black hole is a region of spacetime where gravity is so strong that nothing can escape its pull. Picture the spacetime fabric as a trampoline. When you place a heavy object like a bowling ball on it, the fabric curves downward. Now imagine the ball is so heavy that it creates a deep well, a point of no return. That's a crude way of visualizing a black hole. The concept of black holes is not just theoretical. Astronomers have identified numerous black holes in our universe, and their observations align strikingly well with Einstein's predictions. For instance, the Event Horizon Telescope captured an image of a supermassive black hole in the galaxy M87 in 2019. The image showed a bright ring of light bent by the black hole's intense gravity, exactly as general relativity predicted. But black holes are not just cosmic curiosities. They play a vital role in our understanding of gravity and space-time. They challenge our notions of what is possible in the universe. They test the limits of general relativity, and so far the theory has passed with flying colors. Black holes also open the door to even more perplexing phenomena. For example, the theory predicts the existence of singularities, points where the curvature of space-time becomes infinite. This prediction challenges our understanding of physics and has led to a quest to reconcile general relativity with quantum mechanics, the other pillar of modern physics. These extreme regions of space-time, where the fabric of the universe stretches to its limits, provide a unique testing ground for our physical theories. They offer insights into the nature of gravity and space-time and the fundamental structure of our universe. Black holes are a fascinating consequence of general relativity, but the impact of Einstein's theory doesn't stop there. It continues to shape our understanding of the cosmos, from the behavior of tiny particles to the expansion of the universe itself. General relativity doesn't just explain the motion of apples and planets, it's also our best guide to understanding the entire universe. As we delve deeper into the cosmos, we can't overlook the monumental role that general relativity plays in modern cosmology. This groundbreaking theory provides the framework for our comprehensive understanding of the universe's large-scale structure and evolution. When we think about the origins of the universe, we inevitably come across the Big Bang theory. But what's fascinating is that general relativity is the very foundation upon which this theory is built. It's like the architectural blueprint for the universe's birth. According to this theory, the universe sprang into existence from a singularity, a point in space-time where curvature becomes infinite, around 14 billion years ago. The singularity expanded and continues to expand, resulting in the universe we observe today. But how do we know the universe is expanding? Once again, we have general relativity to thank for this realization. Hubble's observation of redshift in distant galaxies, a shift towards longer or redder wavelengths, suggested that these galaxies were moving away from us. This observation, coupled with the predictions of general relativity, led to the conclusion that the universe itself is expanding. So not only does general relativity explain the birth of the universe, but it also provides insights into its ongoing evolution. Moreover, the theory has been instrumental in understanding phenomena like cosmic inflation, the formation of galaxies, and the concept of dark energy. It has allowed us to peer back in time to the universe's earliest moments and speculate about its ultimate fate. So there you have it. From the fall of an apple to the expansion of the universe, general relativity has reshaped our understanding of gravity and spacetime. It's a testament to the power of human curiosity and ingenuity.